Hello everyone, this is Kiran Kumar. I am going to teach you asymptotic notations. So before going to asymptotic notations, let's compare three algorithms running times informally. So let me take three algorithms A1, A2, A3 and their running times are one is n steps, second one 5n, third one is n square steps. Let me execute them for various sizes of inputs like n value 1, n value 100, after the 10 to the power of 9, 10 to the power of 20. That means these two are huge values. So I am running these algorithms over various sizes of inputs. Let's observe them. When n value 1, your algorithm 1, since it is taking n steps, that means one step, because n value 1, it takes one step. So my assumption here, one step takes 1 unit of computer time. So generally, typically computers take 1 nanosecond to execute any operation. So that's why one step will become 1 nanosecond. If your computer is fastest, probably that might take 10 power minus 12 nanosecond. So it depends on the computer speed. So let me take a computer which can do any operation in nanosecond of time. Let's see that. When n value 1, one step will become 1 nanosecond. If second algorithm takes 5n steps, then that will become 5 nanoseconds. And A3, which takes n square steps, when n value 1, it will become 1 square nanosecond. Now when n value 100, little bit moderate input, then that n steps will become 100 steps, isn't it? That will become 100 nanosecond. So here A2 will become 500 nanosecond and A3 will become 10 to the power of 4 nanosecond. The reason 100 square is 10 to the power of 4. Now if you see the differences, so A3 is taking little bit more time than A1 and A2, isn't it? When it comes to n value 10 to the power of 9, you can see the difference very clearly. So for 10 to the power of 9, so this algorithm 1 takes 1 second and algorithm 2 takes 5 seconds, but algorithm 3 takes 10 to the power of 18 nanoseconds. The reason input is 10 power 9, 10 power 9 whole square is 10 to the power of 18. So that's why 10 to the power of 18 steps. Each step is nanosecond. So 10 power 18 nanoseconds. Now that 10 power 18 nanosecond, if I convert into years, that is approximately 31 years. See the difference now. 1 second, 5 seconds, 31 years. Right? So what I want to say is algorithm 3 is taking more time than algorithm 1 and algorithm 2 for any input. If you take very large input, 10 power 20 is very huge number, for that number still, so your algorithm 1 takes 3170 years, algorithm 2 takes 15,000 years, again 5 times. This algorithm 3 is taking 3170 into 10 to the power of 11 years. It's a very huge number if you compare with running times of A1 and A2. So what I want to say is finally, so algorithm 1 and algorithm 2 belongs to same class of time complexities, but when it comes to A3, it is taking lot of time than A1 and A2. So if I have to classify them into two parts, I keep A1 into A2 in one place and A3 in another place. You understand that? But in mathematics, if you see n and 5n, so they are different. But when it comes to algorithms running times, so these time complexities of algorithm 1 and algorithm 2 are more or less same. So now here I need a notation which can say that algorithm 1's time complexity is equal to algorithm 2, but these time complexities of A1 and A2 are smaller than A3. I need a different notation to say that so these two are equal and A3 is different from them. So finally this idea. So asymptotic notations comes into the picture to say that A1 and A2 are same and A3 is different from A1 and A2. So for that we have to study asymptotic notations. Okay, let me begin with asymptotic notations. We have 5 notations. One is big O notation. Second one, we use O symbol for it. Second one, big omega notation. The symbol for that is this one. Then theta notation. Symbol is this one. So fourth one, small o notation. So small o is a symbol for it. The fifth one is small omega notation. So small omega, the symbol for it is this one. So why 5 symbols I will tell you. So in mathematics, to compare two values, we have five symbols. They are less than or equal to, greater than or equal to, less than, greater than. In the same way, in asymptotic notation, to compare running times of algorithms, we have five notations: order, omega, theta, small omega. So what I want to say is, this big O behaves like less than or equal to, this big omega behaves like greater than or equal to, theta behaves like equal to, and small o behaves like less than, and small omega behaves like greater than. So more or less, so these five notations are equivalent to these notations, okay, but not exactly. Okay, so we'll see these notations one by one. Let me begin with big O notation. So first one is big O notation. We use capital O for it. Let me formally define what is big O notation. I have two functions, f of n and g of n. Okay, so I want to compare them. So we can use order to compare them. I say that f of n equal to capital O of g of n. So otherwise belongs to, both are same. I can use belongs to even. So f of n belongs to order of g of n, or f of n equal to order of g of n if and only if f of n less than or equal to c into g of n for some c greater than 0 after n greater than or equal to n naught. So where n naught is generally greater than or equal to 0. So this is the core idea about big O notation, f of n less than or equal to c into g of n. Somehow if you can prove that f of n less than or equal to c into g of n, we say that f of n equal to order of g of n for some constant greater than 0 after n greater than or equal to n naught. Don't worry about this c and n naught. I will show you how to find out c value and n naught. So you just remember this definition and we'll solve one problem related to this big O notation. Example, let's say f of n equal to n, g of n equal to 5 into n. So why f of n equal to order of g of n, we'll see. So f of n equal to order of g of n if and only if this definition is satisfied. Let me write the definition. Definition is f of n should be less than or equal to c into g of n. What is g of n here? 5 into n, isn't it? Let's substitute f of n less than or equal to constant into 5 into n. Can we prove that 5n greater than or equal to n for any c value? That's very obvious, right? If I take c value 1, this is one of the possibility, then 5 into n is greater than or equal to n, right? For what values of n? Any n value, isn't it? Can I say that for any value n greater than or equal to 0, right? So already I said that we have to find out some c and some n naught, so that n is greater than or equal to n naught, second one c greater than 0. If you can find out such values, that's it. So we can say that f of n equal to order of g of n. Here c value 1 and n greater than or equal to 0. This 0 is nothing but for me here n naught. So finally I proved that f of n equal to order of g of n. The reason f of n is order of g of n if and only if f of n less than or equal to c into g of n for some c. Yes, I have shown some c value 1 so that n less than or equal to c into 5n where c value 1. Yes, that's why f of n equal to order of g of n. Let's see one more example related to big O notation. Let's say f of n equal to 2n plus 10. G of n is, let's say, n. So question is, f of n is order of g of n is a question. So we know the definition. If really f of n is order of g of n, then we have to prove that f of n less than or equal to c into g of n for some c greater than 0 and n greater than or equal to n naught, isn't it? Where n naught greater than or equal to 0. Let's try again. So here f of n is 2 into n plus 10. We have to prove that less than or equal to c into g of n. G of n is n. So if you see carefully, we have two n's, we have after all one n, but we have to prove that this component should be greater than or equal to this component. For that you should take C value suitably. So my common sense says that C should be more than 2. Let me take C value 3. Then 3n greater than or equal to 2n plus 10 is quite obvious, isn't it? Let's simplify it. So 3n minus 2n is n greater than or equal to 10. Whenever n greater than or equal to 10, this equation is correct. Whenever this equation is correct, this equation is correct. Whenever this equation is correct, this equation is correct. Then this equation is correct. Isn't it? So finally f of n equal to order of g of n for n greater than or equal to 10 and c value 3. So already I told you that we have to show some c value and some n greater than or equal to n naught. Here n naught is nothing but 10. So in one line, proving order is simply showing some c and n naught so that this equation becomes true. So simple. Let's see the second notation, that is big omega notation. So omega, big omega. We write like this: f of n is omega of g of n if and only if f of n greater than or equal to c into g of n for some c greater than 0 after n greater than or equal to n naught greater than or equal to 0. So this is big omega notation. So it's exactly like order notation, but the only difference is here we have to prove that f of n greater than or equal to c into g of n. So it was less than or equal to for order. It is now omega greater than or equal to for omega. We'll see one example. So f of n is, let's say, 5n plus 10. G of n is, let's say, 2n. Then the question is, f of n is omega of g of n, true or false? Really f of n is omega of g of n, then f of n should be, according to the definition, greater than or equal to c into g of n, isn't it? So where f of n is 5n plus 10 should be greater than or equal to c value, anything, some constant greater than 0 into gn. Gn is 2n. So use common sense and decide c value. So you have here 5n, isn't it? So here you have c, you should fix such a way that 5n should be bigger than 2n's. So let's take simply c value 1, then that will be obvious, right? So 5 in plus 10 greater than or equal to 2n. So that is only possible if 3n greater than or equal to 10. I am simplifying it. 5n minus 2n is 3n greater than or equal to 10. Then n should be greater than or equal to 10 by 3. That is nothing but 3.3. So after n greater than or equal to 3.3 for c value 1, this equation is correct. That's why f of n is omega of g of n. You understand? Let's take one more example. F of n is, let's say this time, n square. G of n is n square plus n. It looks like g of n is bigger than f of n, isn't it? Yes, but still f of n is omega of g of n. Why? We'll see. I know only one definition, this one. Let me substitute it. So here we have to prove that f of n greater than or equal to c into g of n. So where f of n is here, n square should be greater than or equal to c into g of n. G of n is n square plus n, isn't it? So I use some common sense here. I have to prove that n square is bigger than some n square plus n's, right? If you take c value 1, so you can't prove because we have n squares and some n's. To dominate this n square plus n, the c value cannot be more than 1 or equal to 1. But we have possibility of taking c greater than 0, then let's take a number between 0 to 1. So simple. So let me take 1 by 2, just it's a guess. Okay, if I take c value 1 by 2, what happens? Let me observe. N square greater than or equal to half of the n square plus n, right? Now this n square I write like half of the n square plus half of the n square, and you just observe the right side. It is half of the n square plus half of the n, isn't it? Just compare them now. You have half n square, here we have half n square. Here you have half n square, but here half n. So half n square always greater than or equal to half n, isn't it? That's why happily I can say that 1 by 2 n square greater than or equal to 1 by 2 n, right? Otherwise you can cancel like this, 2 to cancel. So n square greater than or equal to n is obvious for any greater than or equal to 0. So finally I can say that this f of n is omega of g of n, and the evidence for it is c value 1 by 2 and n greater than or equal to 0. Some students ask this question, sir, I got c value 1 by 4, you got c value 1 by 2. That's fine. If you get some c, that's enough, because you know this definition is expecting some c, right? And you might get a different n naught, like you may get n greater than or equal to 10, but finally you should get some c and some, you know, after n greater than or equal to n naught. If your condition is true, after that then we say f of n is omega of g of n. It's so simple. Let's see theta notation. F of n is said to be theta of g of n if and only if this f of n is in between some c2 into g of n and c1 into g of n for some c greater than 0 after n greater than or equal to n naught. So theta notation is very easy after understanding order and omega. The reason, if you see carefully, we have to prove two cases. One is f of n less than greater than or equal to c1 into g of n. Second one, f of n less than or equal to c2 into g of n. So condition number 1, if you prove, let's say condition number 1 is f of n greater than or equal to c1 into g of n. Somehow if you prove it, and condition 2, which is f of n less than or equal to c2 into g of n, then you are proving that f of n is, this is nothing but f of n equal to omega of g of n, isn't it? So f of n less than or equal to some constant into g of n, it's nothing but proving f of n equal to order of g of n. So in one more way I can say that f of n equal to theta of g of n is nothing but f of n equal to order of g of n and f of n equal to omega of g of n. So already we know how to check order and omega, so that's why we can check easily theta. Example, let's say f of n equal to n square plus n, g of n equal to, let's say, 5n squares. Are they same? We'll see. That means f of n equal to theta of g of n is a question. Really f of n equal to theta of g of n, then f of n should be order of g of n, f of n should be omega of g of n. Let's see one by one. Let's say first one, we'll take f of n equal to order of g of n. Let's try it. So here f of n is n square plus n. We have to prove that equal to order of g of n. What is g of n? 5n square. Really n square plus n is order of 5n square. According to the definition, it should be n square plus n less than or equal to some constant into 5n square. Let's apply some common sense. We have to prove that right thing should be greater than left thing or equal to. Already we have enough n squares. Here you have only one n square. Then by taking any c value like c value 1, we can achieve it, right? So let's try that. So 5n square should be greater than or equal to n square plus n. So that's obvious, right? The reason, if I simplify it, you get 4n square greater than or equal to n. This is always true, right? For any n greater than or equal to 0. So this 0 is nothing but n naught, and we got some c value. Right? So I proved that f of n equal to order of g of n. Let's try f of n equal to omega of g of n. Here f of n is omega of g of n. What is f of n again? F of n is n square plus n. We should prove that greater than or equal to c into g of n. G of n is 5n square. This is omega definition, isn't it? greater than or equal to. So n square plus n greater than or equal to c into 5n square. Here if I use my common sense, so you have n square plus after all n, but right side we have 5n squares, but still you should dominate that 5n squares. For that c should be a value which is less than 1. That means you take, less than 1 anything. So to cancel 5n squares, better we can take c value 1 by 5, so that they will be cancelled, right? So you end up with, if I take c value 1 by 5, then that this 5 will be cancelled and you end up with 1n square. Still we have left side n square plus n that can dominate your c into 5n square. So now I got c value 1 by 5. In that way, based on the equations, I fix c value. So n square plus n greater than or equal to, so c value 1 by 5 of 5n square. If I simplify it, you get n square cancel, you get an equation called n greater than or equal to 0. That means this equation is correct for any value n greater than or equal to 0 for c value 1 by 5. So finally I proved that f of n equal to omega of g of n, f of n equal to order of g of n, hence f of n equal to theta of g of n. In that way we can check whether f of n is order of g of n or omega of g of n or theta of g of n. These are all about important notation called order, omega, theta. Let's see some of the numerical problems related to order, omega, theta. Let me take f of n as n square plus 5n plus 100, g of n equal to n square. So I am going to prove that f of n equal to order of g of n. So you know the definition that f of n is order of g of n, then f of n should be less than or equal to c into g of n, isn't it? So that's why order behaves like less than or equal to in the mathematics. So more or less we are proving like this, f of n less than or equal to g of n, but not exactly less than or equal to. We are proving that f of n less than or equal to some constant into g of n. So that's why I say that order behaves like less than or equal to in mathematics. Now n square plus 5n plus 100, how it will be less than or equal to n square? Generally in mathematics it is not possible, but in asymptotic notations we have to prove c into g of n. Then that might be possible. Let's try. So we have to prove that n square plus 5n plus 100 less than or equal to c into n square. So we have to plan c value. So first, without c, you have n squares left and right, but left side we have 5 n's and hundreds. That value, that means right side you don't have that 5n and 100, but still we have to prove that right side is bigger. So to make right side bigger, c should be sufficiently large. I will tell you what is the c value you should take. This 5n is at most n square, isn't it? This n square is at most n square. This 100 is at most 100 n squares, right? Not more than that. So I am exaggerating the values. So n square becomes at most n square. This is at most 5n squares. This is at most 100 n squares. So overall this entire equation cannot be more than 100 plus 5 plus 1, 106 n square. So that's why I take c value 106. If I take c value 106, so confidently I can say that this 106 n square is greater than or equal to this value, isn't it? So finally we prove that f of n equal to order of g of n. We'll come to second one. F of n equal to n square and g of n equal to n square plus 5n plus 100. So question is this f of n equal to omega of g of n? Is a question. So how I answer you? See, f of n greater than or equal to c into g of n is the formula, isn't it? F of n is n square. Here we have to prove that greater than or equal to c into n square plus 5n plus 100. This time challenge is we have left hand side smaller value but right hand side bigger value. Such smaller value should become a bigger value than this right side. By planning c value we should make it. So what I do is this c, I can take anything. I can take c value 1 by 2. Let's try a c value 1 by 2. I will tell you the reason. If I take c value 1 by 2, then almost this 1 by 2 value is reducing this n square to half, so that you get edge at left side. N square greater than or equal to half of the n square plus half of the 5n, that means 5 by 2n, plus half of the 100, which is nothing but 50, isn't it? Now if you see this one, that means we have to prove that n square greater than or equal to half of the n square, right, plus of course 5 by 2n, 2.5n plus 50, right? Now let me simplify. If I cancel these two, you get half of the n square left side, half of the n square greater than or equal to 2.5n plus 50. So what I want to say is, this equation is definitely correct after some n value. Okay, why? Because let me further simplify it. This is nothing but n square greater than or equal to 2 into 2.5n, 5n plus 2 into 50, 100. Why this equation is correct? The reason, n value 0 I may not be correct, n value 1 I may not be correct, but when n value 10, just observe, 10 square is 100 greater than or equal to 5 into 10 plus 100. Still I am wrong, right? 100 greater than or equal to 150 is wrong. But if I take n value 20, just randomly I am trying, 20 square, which is 400 greater than or equal to, so 5 into n value 20 plus 100, so it is 100 plus 100, 200. Yes, 400 greater than or equal to 200. What I want to say is, this equation is true after n greater than or equal to 20. Initially it may not be correct, but after n greater than or equal to 20, you observe n square definitely greater than or equal to 5 into n plus 100. The reason is very simple. N square is n into n, but this is after all 5 into n. 5 into n cannot be better than n into n after some n, isn't it? That's why this is such n. After this, definitely n square greater than or equal to 5n plus 100. So whenever this is true, this is true. 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 This is true. Finally, this is true. So we proved that f of n equal to omega of g of n. So finally, we proved that f of n equal to order of g of n here, and f of n equal to omega of g of n. So now we'll see the summary. Though you have a bigger equation, like it looks value wise, it looks bigger than this one, right? Still we were able to prove that f of n equal to order of g of n. In this process, you realize that this 5 n's and 100 doesn't matter, right? You can have 5 crore n's. Still, by carefully planning c value to 5 crores, we can dominate this left side value. So these lower order terms, these are all called lower order terms. These lower order terms never give any support to n square. So that's why, so though we have 5n and 100, it's like nothing we have. We have after all n square. Right side we have n square. That's why we can prove that n square less than or equal to n square, right? So that's the reason n square plus 5n plus 100 is less than or equal to c into n square. So summary, lower order terms never help you in the process. Similarly here, these lower order terms never help you. Just compare this n square and n square. Since n square is greater than or equal to c into n square, that's why n square is omega of g of n. From now onwards, by removing lower order terms, you compare the remaining functions. Whatever the result holds good over there, same thing holds good if you have that lower order terms in the equation. So let me put it in another way. That means if f of n is example, whatever example, n to the power of 5 plus some lower order terms, lower order. Okay. If you have g of n equal to n to the power of 5 plus anything, lower order term. So lower order. It should not be more than n power 5. Then f of n is definitely order of g of n. For that, we don't need to consider this lower order terms. Directly consider n power 5 and n power 5. Question number 1. Is this n power 5 less than or equal to c into n power 5? Yes, that means f of n is order of g of n. In the same way, this n power 5 greater than or equal to c into n power 5? Yes, that's why f of n equal to omega of g of n. That's the reason f of n equal to theta of g of n. We know that f of n equal to theta of g of n means f of n equal to order of g of n and f of n equal to omega of g of n. In that way, so we can solve questions related to this order, omega and theta.